Hi there, it's Prashant, and today we will be talking about variational quantum eigensolver. Quantum computing is an exciting field, but it hasn't matured fully, and we are far away from running the popular algorithms on the quantum computers. We are in the NISQ era of the quantum computing where nothing really works. Well, not really. NISQ stands for Noisy Intermediate Scale Quantum. At the moment, the quantum computers are prone to a lot of noise. For example, every single time you apply a gate, noise will creep in, and the gate you wanted to apply would change into something else. And that is only one of the problems with the noise. Second, the qubits that are generated, they don't really live for a long time, and after a while, whatever information was stored in them or in the system, it must be lost or would have gotten corrupted. It limits the number of operations that you can perform. Moreover, on top of that, we don't have a lot of qubits. IBM has a 433 qubit system that was designed last year. With these limitations, researchers have started to look for the near-term solutions on the near-term quantum devices. These solutions use both classical and the quantum computers to create solutions to various problems. This domain is called the quantum machine learning, and it has applications from finance to chemistry and from climate modeling to physics. Variational quantum eigensolver is one such near-term algorithm. The process starts with a Hamiltonian. The Hamiltonian is named after, I think, William Hamilton, definitely not after the play Hamilton. And it is the definition of the problem we aim to solve in the form of a matrix of number. The matrix is a Hermitian matrix, which means that it's equal to its conjugate transpose. Goal of the VQE is to find the lowest possible eigenvalue for a given Hermitian matrix. So what exactly is an eigenvalue? Well, I won't go into much detail, but when you multiply a matrix with a vector, then the vector rotates in space and scales up or down compared to the original vector. If there is a vector which, when multiplied to the matrix, would only cause scaling effect but not rotation, such vectors that go through pure scaling without rotation, they are called the eigenvectors, and to that particular matrix, and the corresponding scaling factor is the eigenvalue. Now, why we are interested in the lowest possible eigenstate for a system, be it a molecular one or a financial one? Because it gives us the configuration of how the system is set up, and we can use it later to simulate it in real time. The next step after the Hamiltonian is the NSATS. NSATS is the German word which means approach, and in the mathematical and physics world, it means an educated guess. This educated guess is dependent on a few parameters. The NSATS would take these parameters and would create a quantum state. This, in general, is in the form of a circuit which has quantum gates. The focus of the NSATS is always on estimation of the eigenvalue of the Hermitian matrix. The NSATS chosen should not be very deep. That is, computing costs should not be too intensive, and it should cover as many possible quantum states as the system could be in. Also, NSATS shouldn't take too many parameters. After we have estimated the eigenvalue, the classical computers come into picture. The classical computer work on optimization part of the problem. What it does is update the parameters so that we will get better eigenvalue. The quantum system take these updated parameters and calculate the new eigenvalues. This process goes on iteratively, so we get lower and lower expectation value. Then we put these values back to the quantum part and reiterate. Essentially, VQE is an optimization algorithm that's running partly on quantum and partly on the classical system. Why VQE works is because of the variational principle. It states that for a given Hermitian matrix, its expectation value must be equal to or greater than the lowest possible eigenvalue. It means that if we keep minimizing the expectation value, then we will keep getting closer to the minimum eigenvalue, but never below it. So this was the theory part. Now let's see if we can apply the steps that we had described above and can code it in Python. Let's see. All right. So the first thing that I want to do is maybe write all the steps so that we know what exactly we are doing. Yeah, this is the markdown, so /array and this will be li, right, and this would be li. This is a painful process, but I think it would be a good thing to do so. So define the Hamiltonian, and then actually let's just do it one more time, li, and then li. I don't know the shortcuts of Markdown, so just bear with me. And so first we define the Hamiltonian, then we find the lowest state, which the reference value, let's call it. After that, what we are going to do is define parameters for ansatz, and then we will define ansatz. Once we define the ansatz, we have to take some measurements, and that would be define measurements, and it would have some of the parts, and within it would be define the circuit block, and yeah, and after we define the circuit block, we should be measure on the quantum computer. And then I think after that we we basically will be defining the expectation value. From the measurement results, right? And come on, and that is it, I believe. Oh, come on. And then okay, there should be something more. Then the classical part starts. Let's run the optimizer, and then find the estimated lowest value. It should be ID value. Lowest ID value, and compare it with the reference value of the step 2. And I guess that is it. These are the steps. Oh, what did I do? Li, define measurements. Did I forget something? Define measurements. Oh, okay, maybe. All right. I also want to mention the paper that was used. I think this Variational Solver paper. I think this is the one. So let's just use this. After this, use this. Now let's call the imports. I'm not really sure what all imports are required at the moment, but import numpy as np from random import random. Let's say now the first thing that we have to do is to define the Hamiltonian. And okay, yeah, and I think the Hamiltonian, there's a limitation on how Hamiltonians can be used with VQE, and we need Hamiltonians to be constructed as sum of the Pauli operators XYZ, and maybe their tensor product if we are using a multi-qubit system. And let's say it would be of the form, let's say ax plus b y plus c z, something like that. So a, b, c are the coefficients, and we have to calculate these coefficients. Let's use something random. Let's actually scale it. Okay, firstly, what's the value? Let's put, yeah, let's scale it. Let's scale it by a factor of 10. And let's do it for every okay. It was a B, this would be C, this would be D. Okay. A, B, C, D would be okay. Yeah, these are the values. Now what we can do is let's actually, here it is, right? Okay, so we will use the sparse Pauli operator class to define the info Hamiltonian. Import sparse Pauli operator. Let's change the name to demo. Okay. So what we will be doing here is, let's define a variable Hamiltonian sparse operator dot to list here dot from list, and it would be a list. It would contain multiple variables. Because we have 4 different gates, we will use all, and it will have I and comma A. It will have Z with comma B. It will have X with comma C. It will have Y with comma D, and Hamiltonian, let's just, it's of the form AI plus BZ plus CX plus DY. Okay, now let's do. Okay. HMAT, let's see, okay, this is the 6.1331.8.2. okay, I don't know what it is. The next step that you have to do is to find the minimum value, which is the reference value. The reference value, let's call it the minimum value for Hamiltonian is equal to, oh yeah, we need one more thing. So we need basically from Qiskit dot algorithms dot minimum eigensolvers, right? Minimum eigensolvers, import numpy minimum eigensolver. Okay, yeah, here minimum value is numpy eigensolver. We will compute minimum eigenvalue. Come on. And we will calculate the we'll give the Hamiltonian to it. Dot eigenvalue. And then value. So minus 4.17815. So this is the value that our optimizer should try to reach. Okay, that's good. Now we have to define the parameters for NSATs and define what NSATs looks like. Define parameters for NSATs and define NSATs. Okay, let's call the params is np.array and it will be a list. Let's use 2, 3 dot I np.py and also define 21 Okay, so now define the NSATs prep, and it will take place the params, and it would also take circuits, the quantum circuit that will pass to it. Q equals to circuit.qregs and 0 and we have circuit.rx pointers and 0 q circuit.ry params. Let's take the first and we will apply it on the first qubit itself, and same for the which is the pi by 2 rotation .rz params 2. And we will return the circuit. This is now, okay, we have done this. Now we will define the measurements. And first of all, we will create a circuit block. Let's call it the VQE block. and it will take certain things. It will definitely take the parameters, and it will also take the basically what gate do I need to apply to various states. So it will take the I, Z, X, Y. We call them operators. Okay, so I also need one more thing. From Qiskit import quantum register circuit, quantum register, and classical register. Okay. Quantum register is size 1, and then your C is classical register of size 1. Then we have circuit. It's local variable quantum circuit, which will have Q and C. And we will pass this to n sides, correct? To circuit and params. Now we will measure if op equals to Z, then what do we have to do? Well, if op equals to X, what do we have to do? Well, if op equals to Y, then what do we have to do? Okay, in case of this, we just use circuit dot measure and C0. I think we will use this for everyone, each of them, and at the end we will return circuit. Now for X, we will also apply a header mod. For Y, we will dot STG, which will also header mod. I think this is it. Next thing we have to do is measurement on the quantum computer. Okay, so I don't know. Let's first write the optimizer. So optimizer, let's say def VQE opt params. We will input the params, print the params, because these are the parameters that will be updated. We take the Hamiltonian to list, and what we need, okay, let's just do this thing here, Hamiltonian dot to list, and if I want to, I want the real part and this operator part. How do I get it? Let's say so maybe I can just Hamiltonian dot coefficients 0.3, which will, yeah, you can get it like this. Okay, also we are sum let's define a variable. The thing is that we would be running all these parts like C part, X part, Y part, I part differently, like separately. So each of them will have a separate, it's each term in the addition, and they would feed into the circuit sum. So circuit sum is 0 for I in range, let's say length of LS. What we would do is circuit sum equal to circuit sum plus, there's a shorthand, but just for sake of clarity I'm doing this, Hamiltonian dot coefficients I, that is 0th one, and so let's say I want to multiply it with this X basically I have to multiply it with a circuit. So we can call maybe some term, and it will take the parameters, and it will also take, okay, Hamiltonian 0 is this, Hamiltonian dot to list 0 and 0. Okay, so that's how we'll get it. So we already have the list. And then we will do this for all, and we'll just return the circuits. Okay, now we have to define this quantum term, whatever this is. Let's call def quantum term. It will take param, and it will take this hops. If hops equal to I, then return 1, right? Else if hops z, then we have to just call VQE circuit block. Circuit equals to this params hops, and I think it's for all. Z, and there is X, and for Y. Now once we are done with this, we have to basically run the circuit on quantum computer, and oh yeah, so we would need this basic AER from Qiskit import basic AER and execute as well. Also for from scipy dot optimize import minimize. Okay. So this will be backend. Come on. Backend will be basically dot get backend, and we will use a chasm simulator, and job will be execute, and we will give it circuit, we will give it the backend, we will give it the shots equal to shots, and then we will have the result is job dot result, and then counts we will be result dot get counts. Now we will feed this to a function which is def calculate expectation value. Calculate expectation value, and it will take counts. Okay, so we will give calculate expectation counts. Oh, right. It's a typo here. Okay, now it's a simple logic. Let's expectation value is, let's say, 0 for count and counts. What you have to do is sign equal to +1. If count equals to -1, then sign will change to -1, and expectation value is expectation value plus sign multiplied by count at this particular value, and I want shots, which is 819. Oh, it will require shots, so it will require shots, and this will require shots. Okay, the definitions. Oh, why am I making this mistake? Okay. All right. Now these things are done. We have, now let's run the optimizer. Run the so we will call the minimize, we will give it the VQE opt, we will give the params, we will use the method, go below, we will give all is equal to, let's take it into VQE result. Where did I make this mistake? Hamiltonian is quantum term. None type, okay. complex and non-type. Unsupported operand for complex and non-type. Okay, I must have made a mistake. VQE of to list circuit sum and Hamiltonian dot coefficients are dot coefficients Hamiltonian dot coefficients I oh sorry 0. Oh, okay, so I had to take the real part here, right? Real part. Come on. Where did I? Hamiltonian dot coefficients. What's the error? I think I will not put down this value. So use this. Okay. 1.73. This is 1.73. Okay. So, all right. I think we have gotten out. So the value that we had to compare it with was 1.75, and is it? Yeah, it is. It is. Let's just run it one more time. So minus 0.05. Wow, I'm not near that. Minus 5.18, minus 5.30. Yeah, not bad. Minus 2.58. Minus 2.56. Yeah, I think this is it. Let's just print the results. Print estimated eigenvalue from the Hamiltonian from the optimizer is result.fun and the eigenvalue Hamiltonian corresponding to lowest energy is min val. Yeah, minus 2.56. So yeah, this is done. And I think we have successfully carried out all the steps that are required for VQE. And this is for a single qubit system. There could be a system which has XX, XY, YZ, basically the tensor products of the Pauli operators. And I think that would, the steps would remain the same, but something would change in between. But that is beyond the scope of this particular exercise. Let's run it one more time. Let's run it. So remove this. Yeah, the estimated value is minus 10.62 and the reference value was minus 10.67. So we're pretty close. So yeah, this is it. And we have demoed the VQE from step by step according to the paper that was published. If there are any comments and if you have any questions, then do reach out. Thank you.